Hello, and welcome to This Explainer. I am absolutely thrilled to be your strategist for today's session. If you are preparing for your Cambridge IGCSE physics examinations, specifically looking at syllabus codes like 0625, you have landed in exactly the right place. Listen, today we are not just memorizing physics textbook definitions, no way. We are talking about absolute exam mastery. We are diving deep into the examiner's playbook. I want you to think of yourself as a symphony conductor. We are going to orchestrate your understanding of resistance and Ohm's law so flawlessly that every single paragraph you write in that exam booklet acts like a different instrument playing perfect harmony. But before we get to the beautiful music, let's look at the challenge. Imagine a real Cambridge past paper question on the screen right now. It asks you to calculate resistance from a graph and explain the trend. We see two types of students tackle this. First, we have Alex. Alex is the student who overloads the page with raw physics facts. Alex writes a massive wall of text detailing everything ever known about electricity, but there is absolutely no focused analysis. Then we have Sam. Sam is always rushing. Sam sees the numbers, skips the command words completely, throws a random answer down, and moves on. If we put their answers side by side, they are covered in red pen marks from the examiner. Why? Because they lacked a cohesive strategy. So get focused, because today's explainer is designed to transform those red marks into green check marks and completely change how you approach your past papers.
Look at this single number on the screen, 15%. I really want that to sink in for a second because it is an absolute game changer. Our source data reveals a massive high-stakes hook. This single topic of resistance, which includes Ohm's law, the physical properties of wires, and the experimental framework surrounding them, accounts for approximately 15% of the total marks in your physics examination. Think about what that actually means for your final overall grade. 15% can easily be the difference between 2 or even 3 entire grade boundaries. It is literally the bridge between a B and an A star. If you master this specific section, you are building a massive, unbreakable safety net for your entire exam. It is not just a minor subtopic that you can gloss over the night before. It is a foundational pillar of the Cambridge physics assessment.
So, here is our roadmap for mastering this 15%. 1. The core principles of resistance, where we build our theoretical foundation. 2. The method marks strategy, where we learn exactly how to earn every single procedural point available. And 3. The top 3 examiner warnings, where we identify the massive pitfalls that catch thousands of students off guard every single year. Let's dive right into it.
Okay, let's kick things off with Section 1, the core principles of resistance, the theoretical foundation. Now, this is where we reveal the true strategy. To orchestrate a top-tier answer, you need to understand the specific physics assessment objectives. Every command word in a Cambridge paper, words like state, determine, or explain, dictates exactly which instrument you need to play. To master this, top students use what we call the PEEL framework. That stands for point, evidence, explanation, and link. You make your physics point, you back it up with data evidence, you explain the physical mechanism behind it, and you link it right back to the specific context of the question. Keep that framework in mind as we look at the core principles.
Here is your foundational building block. Resistance is defined by the equation R equals V divided by I. But listen, the Cambridge examiners want you to know so much more than just the basic algebra. They are heavily testing your understanding of how this relationship is determined experimentally in a lab. You must be able to confidently articulate that resistance is found using a voltmeter connected in parallel to measure the voltage or potential difference, and an ammeter connected in series to measure the current. The theoretical architecture of this concept rests on your precise definitions and experimental setups. When you write your answers, using the correct terminology is absolutely vital. Remember Alex, who we talked about earlier. Alex just scribbles R equals V over I and leaves it at that, totally missing the command word asking for an experimental description. Don't be like Alex. Examiners are looking for that clear, evidence-based reasoning perfectly structured. Before we continue, subscribe to our YouTube channel, Ace the Exams _IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Let's move into the transformation phase. This brilliantly illustrates another core area where students are heavily tested, the physical properties of a wire. Look at the two sides of this causal relationship. On one side, we have length, which is directly proportional to resistance. That means if you double the length of the wire, the resistance doubles. On the other side, we have cross-sectional area, which is inversely proportional to resistance. If you double the cross-sectional area, meaning you make the wire thicker, the resistance is cut in half. Let's bring back our rushing student Sam. In a past paper, Sam wrote, "Longer wire means more resistance." The examiner marked it with a red pen. Why? Because it lacks precision. Let's rewrite Sam's answer live right now using our physics success blueprint and the PEL framework. Point. the resistance of the wire increases. Evidence and explanation. Resistance is directly proportional to length. Therefore, as the length doubles from 1 meter to 2 meters, the resistance doubles, due to electrons colliding more frequently with lattice ions. Link. This confirms the linear trend shown in the graph. Boom! We just transformed a zero-mark answer into a full-mark, green check answer. Imagine orchestrating your argument like this. Your knowledge of length is the strings. Your knowledge of area is the brass. When you bring them together perfectly, demonstrating both direct and inverse proportionality, you create a beautiful symphony of physics knowledge.
And here is where you really separate yourself from the pack. Direct insider insights from the principal examiner reports show that candidates who reference cross-topic connections achieve significantly higher marks. What does that actually mean for you? It means the theoretical architecture of resistance doesn't exist in a vacuum. The highest-scoring students don't just state facts about wires, they seamlessly integrate these causal relationships with other major areas of the syllabus. When you can take a question about the resistance of a heater wire and connect it to energy transfer equations, or link it to the heating effect of current in thermal physics, you elevate your answer from basic foundational knowledge straight into the elite analysis domain. You show the examiner that you understand how the entire physics universe connects. That is exactly how you secure those elusive top-tier marks.
Which brings us perfectly to Section 2, the method mark strategy, earning every point. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into the interactive workshop part of our explainer. I'm going to challenge you to apply this strategy in real time.
For our first challenge, the data scan. Imagine a complex physics data table appearing right in front of you. It's got different wire materials, varying lengths, bizarre cross-sectional areas, and you have exactly 60 seconds on the clock to extract the core trend. How do you do it without panicking? You use this exact problem-solving framework. Step 1. Deconstruct. You must actively identify the given information before you even reach for your calculator. Pull out the voltage, the current, standardizing the units for length and area. Step 2. Solve. Systematically break the math into logical, sequential steps. Don't rush it like Sam. Step 3. Evaluate. Look at your final number. Check it for reasonableness. Does a domestic circuit wire really have a resistance of 1 million ohms? Probably not. Make justified recommendations based on your evidence. When you orchestrate your answers through this exact deconstruct, solve, and evaluate framework, you are speaking the examiner's language fluently.
Now for Challenge 2, find the flaw. I want you to look closely at this official examiner alert. It says, students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Think about Sam again. Sam writes down a paragraph that just has a bunch of scattered numbers and a final, mathematically incorrect answer. No formula, no substitution. What is the flaw? The flaw is giving up the safety net. Multi-stage physics analysis is tough, and under intense ticking clock exam pressure, it's incredibly easy to make a small, silly calculator error, like dropping a zero or misplacing a decimal point. But if you have used our framework, if you explicitly wrote down R equals V over I, if you clearly showed the substitution of your ammeter and voltmeter readings, the examiner will happily award you method marks for your procedural process. You are literally saving your grade by thoroughly documenting your math. Never, ever just write down a final number.
Let's move to Challenge 3, Speed Writing. You are faced with interpreting data from two different circuits. The examiners require incredibly strict conventions for comparative analysis. You must proactively identify similarities and differences. You need to use comparative connectives in your sentences, powerful words like whereas, conversely, or in contrast. You must support every single comparison with hard numerical evidence extracted directly from the graph or table. And finally, you draw concrete conclusions about their relative importance. Imagine you have 30 seconds to write one perfect PL paragraph comparing these circuits. Point, evidence, explanation, link. Following these bullet points is how you win. Presentation of your information matters just as much as the physics itself. Use proper headings, correct terminology, and clear, structured annotation. You are directing the examiner's eye exactly to where your marks are waiting.
We are in the final stretch now. Section 3, Top 3 Examiner Warnings. Avoid these pitfalls. This is where we bring everything together into our final, ultimate system for exam success. The Cambridge examiners publish reports every single year, and every single year they complain about the exact same things. Let's make sure you aren't one of the statistics.
Let's systematically break down this table of the top 3 mistakes
directly from the principal examiner reports. We are going to counter these with our 3 rules that guarantee top marks. Mistake number 1 is forgetting to include proper format, losing easy marks, missing standard units, failing to label your ammeter correctly in a diagram, or dropping the formula entirely. Our counter rule, the time management matrix. Take the extra 5 seconds to double-check your units before moving on. Mistake number 2 is forgetting to check presentation. If your logical steps are a scattered mess across the page, the examiner simply cannot award you those crucial method marks. Our counter rule here is the rigid application of the Peel framework. Keep it structured. And mistake number 3, this is the big one, providing answers that are not specific to the context given. If the question asks about a specific experimental setup measuring a specific copper wire, your answer cannot just be a generic memorized textbook definition of Ohm's law. You must extract data from the text, interpret the specific relationship of that specific wire, and draw an evidence-based conclusion. Our counter rule, strict command word decoding. Always answer the exact question being asked.
To help you avoid all of these pitfalls and lock in our system, our source material suggests a truly brilliant memory hack. Under exam conditions, when that clock is ticking down, your working memory can get easily overloaded, causing you to blank out on the simplest basics. The trick is to create your own mnemonic using the first letters of the key terms we've discussed today. For instance, you might use DSE to remember deconstruct, solve, evaluate, or invent a quick mental rhyme to remember that length is direct and area is inverse. Locking in these procedural steps and physical properties with a simple, practiced mental trigger ensures that you apply the correct formats and use the right terminology, even when the pressure is maxed out.
So, as we wrap up this session, I leave you with this final provocative question. If you consistently apply the R equals V over I theoretical principles alongside this exact peel and deconstruct, solve, evaluate, examiner framework, how many grade boundaries could you cross? Remember, this topic alone is worth 15% of your exam. By showing you're working, securing those method marks, and avoiding fundamental formatting errors, you are quite literally engineering your own success. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGSC to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGSC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep practicing those past papers, and I will see you in the next explainer.